Wuxia Jing. Wuxia Jing is right now working as an assistant professor in Xi'an Jiaotong University in China. She obtained her PhD in Xi'an Jiaotong University recently, and her research interests include software architecture, code analysis, and microservice. This work that she's going to present is about exploring the architectural impact of possible dependencies in Python software. So it's all yours, Wuxia. You can share your screen with us.
Okay, can you see my screen?
Yeah, I can see your screen perfectly, and I can hear you fine.
Okay.
Excellent.
I will start.
So you can
hello.
start whenever you're ready.
Okay. Hello, everyone. I'm Wuxia Jing. I will introduce our work about exploring the architectural impact of possible dependencies in Python software. Our work motivation is dependencies among source code entities are the foundation for software architecture analysis, such as architecture recovery, architecture anti-pattern detection, and architecture metrics. Code dependencies include call relation, import relation, inherit relation, and so on. For example, in this code, the first line shows that the main file will import module, so there is an import dependency from the main file to module. The first line shows that the f2 method will be called by f1, so there is a call dependency from f1 to f2. In these dependencies, because we can definitely determine which module and which f2 will be dependent by the main file. So we call such dependencies as explicit dependency. The definition is the syntactic dependency relation that's explicit manifested in source code. However, dynamically typed languages like Python tolerate the lack of explicit type references, making certain syntactic dependencies indiscernible in source code. For example, the f1 method has a parameter named object, but the type of object is lacking, so we cannot determine which f2 method will be called by f1 because without running this code. So because f2 is defined both in class B and in class A, due to the possibility, we call such call dependencies as possible dependencies. The definition is the syntactic dependency relation that's not explicitly manifested due to the lack of type information in dynamic typing. Then let's see an example. We use Understand, a commercial tool, to export file-level dependencies from Python code. This Python code includes eight files, and the matrix shows the dependency matrix. For example, each line and each column corresponds to a file, and the mark in one cell means that the file in this row will depend on the file in its column. We use blue mark denotes the explicit dependency, and use red mark denotes the possible dependency, which is missing by this tool. Because dependencies are the foundation for software architecture analysis, so one question in our mind is that to what extent will these missing possible dependencies will impact software architecture analysis? Our work will study this question. Concretely, we study 4 research questions. First, what's the proportion of possible dependencies since they are missing? And to what extent will they impact the dependent structure of a software system? Second, to what extent will the ability of capturing code chain relations be altered when considering possible dependencies? Third, to what extent will possible dependencies impact the subspace structures of a system? And last, we will investigate to what extent will possible dependencies impact maintainability. We conducted this empirical study on Python projects collected from GitHub, and we use understand tool to export file-level explicit dependency, and we denote the result as DE. We also developed a static analysis tool based on array to extract file-level possible dependency. We denote the result as DP1. We also verified against the benchmarks based on the. We also verified our tool against the benchmarks collected from the traces. This figure shows the verification results on 4 Python projects. Let's see our study results. First, what's the proportion of possible dependencies, and to what extent will they impact the dependency structure? Our statistics show that possible dependencies, that is DP1, represent at least 28% of DE compared with DP1. It means possible dependency represents a significant proportion. We also use WC Limbo ACDC techniques to create the dependency structure based on the dependencies. Our results show that possible dependencies make the created dependency structures different from those created by DE only. The average difference is about 30%. The second research question is, to what extent will the ability of capturing code change relations be altered when considering possible dependencies? For the code change relations, if a set of files are often committed together in reviewing history, then there are code change relations among these files. We use DE and the DE compared with DP1 to capture the code change relations, and we measure the precision, recall, and F1 measure, and F1 scores. The figure results show that adding DP1 to DE can significantly improve the precision, recall, and F1 scores when capturing code change relations in reviewing history. The results indicate that possible dependency is an important factor to cause code change among files. Let's see our third research question. To what extent will possible dependencies impact the subspace structures of a software system? For the concept of the subspace structure, we use an example to introduce it. In this example, this matrix shows the dependency structure among 8 files. Then we can use one file as a leading file, such as for example, the car element. We use car element as a leading file, then we can get its subspace. Its subspace includes some elements. First, the car element itself, and other files that directly and indirectly depend on the car element, and the dependencies among those files. These elements construct a subspace. Then for each project, we can, based on each file, to get its subspaces. Our summary on the subspaces reveals that the file sets within about 23% of all subspaces are drastically changed after considering possible dependencies. And also, the dependency sets within 26% of all subspaces are drastically changed after considering DP1. We also compared the files involved in DP1, that is, possible dependencies, and the files involved in DE. We found an interesting observation, is that a fail involved in DP1 has the potential to influence about 28% more fails and 42% more dependencies than a fail involved in DE. And last research question, to what extent will possible dependencies impact the maintainability of a software system? We measure the maintenance cost of a fail from 6 aspects. They are the commit times, the length of the code when changing this code, and the issue number, the issue fixing related commit times, and the issue fixing related lines of code. These values are bigger than the maintenance cost will be large. We compare the maintenance cost of a fail involved in DP1 and with the maintenance cost of fail involved in DE. Then we can get six key values. Our summary reveals that on average, a fail involved in possible dependency incurs about 32% more maintenance cost than that of dependencies. Our results have one implication, that is, possible dependencies are more difficult to manifest in source code, and thus more difficult to understand and to change. Consequently, possible dependencies will incur more maintenance cost than explicit dependencies. Now we want to look at if without considering possible dependencies, then the dependency-based matrix, how the dependency-based matrix will be impacted. We use two metrics for this study. One is decoupling level. Decoupling level assesses how well fails are decoupled into independent modules. On the contrary, propagation cost measures how tightly coupled a system is by calculating how changes may propagate through dependencies among fails. The value of DL is larger and the PC value is lower, then the maintainability of a system will be better. Then based on DE and the union set of DE and DP1, we can get two groups of scores in terms of decoupling level and propagation cost. Then the question is, which group of scores can better reflect the real maintainability of the system? To do this, we measure the maintenance cost based on review history as the ground truth. Then we did a correlation analysis between the history-based ground truth and the dependency-based measures. Our results show that adding DP1 to DE makes the scores can more accurately reflect the real maintainability of the system, because the correlation strength is improved both for deep decoupling level and for propagation cost. Our empirical study results can suggest some implications. First, our results show that possible dependencies has a substantial impact on software architecture structure and maintainability. So we indicate that architecture analysis techniques should account for possible dependencies. Second, type inference techniques have been, even though type inference techniques have been widely studied, but we have checked architecture analysis tools such as Divide and Depends. They have not considered possible dependencies for architecture analysis. We have reported our results to these tools. They verified our findings and decided to include possible dependencies for tool enhancement. Third, our results also show that possible dependency is a major factor to cause code change relations among files in reveal history. So we indicate that supplementing possible dependencies will improve the performance of change prediction related research for dynamic languages. And last, we suggest that developers should be aware of code objects with possible dependencies when changing code. They can do this by highlight such objects by type hints. Now we can make conclusions. Our study reveals that substantial impact of possible dependencies, indicating that architecture analysis and tools should assess and even emphasize the architectural impact of such dependencies. Our contribution have 4 aspects. First, we develop a tool to extract possible dependencies from Python code. Second, we contributed a benchmark for the research of possible dependencies. Third, we reviewed the evidence of substantial architecture impact of possible dependencies. And last, we illustrated the benefits of considering possible dependencies. That's all for my presentation. Thanks. Any questions?
Yeah, thanks for the talk. So I'm checking Huba. So if you have any questions, please feel free to unmute yourself and ask the presenter, Wuxia, or you can type in the Zoom chat in the Huba as well. All right, so I will just ask a few clarification from myself. So I noticed you talk about a subspace structure concept. That is something I'm not so familiar with. Maybe you can tell me more about it. What does it mean that the files are in the subspace? Is that like a module thing?
Okay.
So what does it mean those files are in the subspace, and how can we utilize this subspace structure for other software engineering tasks?
Yeah, the subspace is based on the theory of design rule theory. For example, this example shows the subspace. The left figure shows the dependency structure of 8 files. Of 8 files, the subspace can be get by splitting this dependency matrix. For example, we can use one file, such as car element, as a leading file. So we can get the other files which are directly and indirectly depends on car element. So we can split out 5 files. Then the file files and the dependencies among them can construct a new dependency matrix. So the new dependency matrix constructs a subspace. This is a subspace concept.
Okay, I see. So does this one subspace contribute to one module in the architecture, or?
Yeah. One subspace, for example, in one subspace, we can clustering the files into some modules.
I see.
Yes,
I see.
in some modules. Yes.
I see. Yes. Let's see a bit if they. So we are in Q&A. So if you have any confusions or clarification you need, or discussions, feel free to unmute and join us in the question here. So also my next question would be, so how do you, what's your current next steps for the this possible dependencies? Would you think that maybe for some of them, they are like the true dependencies that you actually think it will worth having techniques to categorize them, and they will have contribute differently to these maintenance tasks. And some of the architecture construction tasks you have experiments in this work.
Yes, we are now doing two things. First, for the benchmark, let me switch the slide. Because we develop one work we are doing is that we are now collecting more benchmarks to verify our possible dependency extraction. Yeah, this is one work, and another work is that because dependencies are the foundation for many architecture analysis, but in paper we just do the forest questions. We are now trying to investigate how the possible dependency and the explicit dependency will impact the architecture anti-pattern detection. Architecture anti-pattern detection relies on the syntactic dependency and other co-change relations, and we have some initial findings. For example, we found that the possible dependencies can the fails detected by the fails involved in anti-patterns when considering possible dependencies, and these infected fails by the anti-patterns incurs more maintenance costs than other fails. Yeah, this is one new findings.
Yeah, okay. Thank you for your participation here in this session. And I think that will conclude this session. And I want to thank all of you for attending and presenting, especially the presenters. And I look forward to maybe seeing you guys next year in person, hopefully. And have a good day or good evening.